Benzene chemically can be called as cyclohexa 135 prime. So this is the molecular formula C6H6 of benzene. These are the two alternate structures suggested by Kekule and which are now universally accepted with alternate double bond systems. This is a planar hexagon wherein the CC bond length is nearly 140 picometers and the bond angle is 120 degree radians. These are the sigma bonds. This is the pi orbital overlap picture. This is the delocalized pi system, and this is the most simplified depiction of benzene ring, which you can also term as a resonance hybrid. The general physicochemical properties or physical properties of benzene, particularly smaller mass, is 78.11 gram per mole. Appearance: when it is freezed, it appears as solid crystals or flakes. However, at ambient temperature, it is a low density liquid. It is a strong odor. Its melting point is 5.5 degree and boiling point is 80.1 degrees centigrade. Its density is lower than water, 876.5 kilos per liter or cubic meters. It is a potential carcinogen and is flammable. It is used as a solvent. It used to be used. Nowadays it is replaced by toluene, but it is a petrol additive as it increases the octane rating and reduces the knocking. Let us see the structure of benzene. As you can see, 6 carbons, 6 hydrogen and conjugated alternate double bond system. It's an important organic chemical compound with a chemical formula of C6H6, comprises of 6 carbon atoms joined in a regular hexagonal ring with 1 hydrogen atom attached to each carbon atom. Because it comprises only of carbon and hydrogen atoms, it is classed as hydrocarbon. Various formulae have been proposed starting from left to right. You can see in 1867, Claus proposed this formula. Dewar in 1867 simultaneously proposed this formula. Ladenburg proposed this formula. Armstrong proposed dated bond formula. Hill proposed this formula, and Kekule in 1865 proposed this formula. Both Hill's and Kekule structures are accepted today. There are other alternate structures also. A 5-member system with an exocyclic bond, or straight chain compounds with triple bonds and double bonds. But finally, they have all been ruled out. Let us discuss further the structure of benzene. Kekule's formula of structure 1 of benzene has been most accepted, and because it satisfies the various questions posed for the substitution products formed to various reactions from benzene. Kekule proposed 2 structures having alternate single and double bonds. This and in other things, their positions have been shifted, and each carbon attached to 1 hydrogen. Further, since benzene has alternate single and double bonds, you can definitely think that there are 2 carbon-carbon bond lengths CC single bond, CC double bond, and so it is expected that the standard bond length can be for the single bond 1.53 Armstrong and CC double bond can be 1.33. Surprisingly, the CC bond length in benzene is neither of these two, but it is intermediate and it is actually 1.39 Armstrongs. And another surprise is it is all across the 6 carbons. So neither the bonds are single or double, they are all having a bond length which is intermediate of the expected single double bond lengths. In short, it can be said benzene is a regular hexagon with identical angles. We'll come to that. And with identical, regular means it's identical bond length, and with a molecular formula of C6H6. When all 6 carbon-carbon bonds have same length, that is 1.35 Armstrong, which is intermediate of sp-sp single sp-sp double bonds and sp3 single bonds, and that is basically between 1.46 and 1.33 Armstrongs. So this is a real picture of benzene. Bond angle is 120 and all across the carbon-carbon is 1.395 and carbon-hydrogen is 1.08 Armstrong. So therefore the structures of benzene can be shown as below. Average of the first 2 structures can be the most simplified structure. So at any given time you don't have to bother which is a double bond or which is a single bond. And actually in reality benzene doesn't have double bond, or neither it has a single bond. It has a bond which is intermediate length between the double and single bond. So many a times if a question is asked, is benzene unsaturated, or in other words, does benzene possess a double bond? Answer is no. And therefore, many a times if you do the simple states of unsaturation, which you do in your organic spotting experiment, that is decolorization of bromine water, or say the biased test of decolorization of the alkaline KMnO4, they fail with benzene. Because the fact is, benzene does not have a double bond. I am talking about carbon-carbon. Neither it has a single bond. It has some bond length which is 1.395 Armstrongs, which is intermediate of the double and single bond. Let us take the orbital picture of benzene. Structural structure of benzene suggests that each carbon atom should be trigonal and therefore sp2 hybridized. This means that each carbon atom has a 2p orbital, and because benzene have the axis of all 6, because of the flat nature of the benzene molecule, axis of all 6 2p orbitals of benzenes are parallel, and these 2p orbitals can overlap the bonding of the molecular orbital of lowest energies as given below, like this. 2p orbitals, and there is a lateral overlap. Or alternatively, this is a sideway overlaps. Alternatively, their positions can shift like this, and so you can deduce both the structures. If I put it in 3 dimensions, this is the overlapping, and then because this can be either this or it can be either this, so in general they all mix, and these pi electrons get delocalized across the whole benzene ring on its upper side as well as lower side. So you can say benzene has pi clouds floating above and below that benzene ring. So each carbon of benzene has a p orbital, and the overlap of these two p orbital forms a cloud of electrons above and below the plane of benzene ring. This is a cloud. The electrostatic potential map for benzene shows that all carbon-carbon bonds have the same electron density. It's uniform. So no carbon is different than the other. Let us see the stability of benzene, which is attributed to its resonance energy. Chemical reactivity of any compound is measured in the term of its standalone energy of formation, that is, or heat of formation, that is delta HF. As I said, benzene is a cyclohexadiene. The delta HF for a double bond is 28.6 kilocalories per mole. So if we have three double bonds, so it is expected to multiply by 85.8 kilocalories per mole inverse. However, as you can see, cyclohexane has one, so it has got 280.16, 28.6, while cyclohexadiene has almost double, 55.4 kilocalories per mole. But in real practice, instead of 85.8, benzene has only 49.8 kilocalories per mole, and therefore there is a difference of 36 kilocalories per mole less energy, and so benzene can be said to be stable by 36 kilocalories per mole, or it contains 36 kilocalories per mole less energy, and this energy difference of 36 kilocalories per mole is called as empirical resonance energy, or RE, of benzene, and this RE is the energy by which benzene is stabilized, and it is therefore an energy that benzene is missing out. And let us understand, therefore this actually answers why benzene is stable, and we will understand more about what is resonance and aromaticity in the next video. Thank you very much, but do connect with us to understand what is resonance and aromaticity in details with multiple examples. Thank you.